All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. People are still trickling in here. Let's jump into it. Last time we spoke about probability, how to find probabilities. And I don't know if we should do a quick recap. I'm not sure. People are still trickling in here. What were we doing? Okay. All right, so last time we defined random experiments, sample space, events, equally likely events. We defined probability, how we're going to find it, the main idea, that of the relative frequency idea of probability. Did an example here, and I told you about the basic process for finding probabilities. So you want to know what your sample space is, create a sample space if possible, which tends to be the hardest step. And we might, as I mentioned here, discover tips and tricks and formulas to avoid doing this. But at the end of the day, you do want to have some idea of what your sample space is doing, some idea of what the event you care about is doing, because you do need to find the sizes of each. That's step 3. And then you divide them, and that's your probability. We also had axioms of probability. So there are 3 basic axioms that we will consider to be true at all times. The probability is always a number between 0 and 1 inclusive. The probability of the entire set is 1. The probability of the empty set is 0, always. The probability of other events might be 0 as well, but those two at minimum are 0 and 1 respectively. In fact, axiom 2, the probability of the entire set is 1. It lines up with axiom 1. Well, it lines up with our definition of probability. And axiom 3 is if you have disjoint sets of the sample space, disjoint subsets, then the probability of the union of disjoint sets is the sum of the probabilities. These are all very important. We also had the law of disjunction, the probability of how we find a union in general of 2 sets. The formula gets a lot more complicated when you have more than 2 sets. We also defined something called the complement probability. Very important idea in the sense that it can really cut down on the amount of work you have to do. It turns out that sometimes finding what you don't want is a lot easier than finding what you do want. And so you can actually find the probability of what you want in terms of the probability of what you don't want. So you just kind of think of what is the opposite of what I'm trying to find. And sometimes that thing is actually easier to conceptualize, easier to count. So we had the complement probability. And we did some examples. And I left you guys with some examples to try. Hopefully you tried them. Otherwise, test 2 might not be so great. But what we're going to do is we're going to go through these guys. And I think for most of them, I'm going to do them several ways, just so you can see several different approaches. Off the bat, I don't think any one approach is more or less superior to the other. I wouldn't necessarily recommend one over the other. I would recommend you do what comes easier. However, I would say that there are some methods that they don't lend themselves very well to being repeatedly used. So if I give you a problem with multiple sections, like some of the problems have here, there are some methods where if you use that method, you kind of have to do all the work from scratch for every part of the problem. Whereas with other methods, if you kind of set it up more generally, and then you can just answer all the questions from your original general setup. So there might be some advantages to some methods there, but we'll see that as we move on. For now, let's just do some probability. Okay, it's what we've all been waiting for. So moving on to problem 1. A fair coin is tossed 3 times. We've seen this already, right? We've seen this. We're going to start off easy. You know, I got you guys. I'm not going to like kill you on the first one. What is the probability that you'll get exactly 1 head? Is part A. What is the probability that you'll get exactly 2 heads? What is the probability that you will get at most 2 heads? So we'll do these several ways. feels. I think it's how much I'm magnifying it. Sometimes this just seems too thin to me. Sometimes it doesn't feel. Okay. First, with the more, first with the methods more conducive. Is that an S or a C? To doing multiple problems from a single setup. So these would be like table would be one such method. So let's look at A. We want the probability of exactly one head. So what we would do is we would, let me actually do the table. So we know here that that S equals the sample space. Think of it as the coin tosses. So it's X, Y, Z, such that X equals H or T, Y equals H or T, Z equals H or T. So it's the set of all triples, right? So it can be heads, 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 tail, heads, etc. But the idea is now we want to count the size of the sample space. So, and of course, I would rather do tuples better than sets because we want to allow repeats. So I'm thinking of this as coordinates, more or less. So this would kind of tell you that the size of the sample space is equal to 2 cubed by the multiplication rule. So there are 8 possibilities here because this is the number of ways you can create a tuple where each entry, 3 tuple where each entry has 2 elements, 2 possibilities. So I know there are 8. We also know that there are 3. So what I'm doing is I'm kind of telling you where the table is coming from based on some theory that I gave you before. We also have 3 entries or stages. So this means our table is a 8 by 3 table. So 8 is the number of rows, and this is the number of columns. All right, so I told you about the general theory of how to set up tables last time. The total number of possibilities is the number of rows you should have. The total number of stages is the number of columns you should have. So ultimately from this, you should be able to say, well, there are 8 possibilities because I have 3 tosses and there are 2 options for each toss. Multiplication rule tells me there are 8. So I know I need a table with 8 rows. There are also 3 separate tosses. Those are the 3 stages. Those are the 3 entries that would go into the coin toss. Therefore, that is the number of columns. So you can get to the table by doing those guys. One, two, three, 4, 5, 6, 7, 8. All right, so this is toss 1, toss 2, toss 3. And I tell you guys how to fill this out. You alternate every one on the most right column. HT, 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 HT. Alternate every 2 on the second one. H, TT, HH, TT. Alternate every 4. HHH, TTT. So we have that. And that represents all possibilities. Now, let me just label these rows here. Row 1, 2, 3, 4, 5, 6, 7, 8. Okay, that will make it easier to do this. However, for something like this, I would expect you to be able to just jump right to the table. I wouldn't really need you to explain all of this. Maybe the size of the sample space, but I think if you can do the table, just jump to the table. You should be able to just jump to the table. I just went through that for the benefit of those who don't know how to construct a table or what size the table should be or blah, blah, blah. I've already explained all this, but I just went over it again as another review. But you should, just by reading this problem, be able to jump to this table. Just know, oh, I need 3 columns, 1 for each toss, and I'm going to have 8 options. It's kind of something I would expect you to know relatively quickly in the future. Okay, so now that we have that, answering these questions should be relatively straightforward. So the first one is we want to get exactly 1 head. So now we'd look at how many ways can you get exactly 1 head? We can in row 4, row 6, and row 7. Probability of exactly 1 head. Then the size of A equals 3, because this can happen in 3 ways. You can see rows 4, 6, and 7. So this means the probability of A is 3 over 8. Now, once you do that initial setup, everyone else is just pretty much as easy. So B, let B equals the event. What do we want? You'll get exactly 2 heads. Note, this is actually equal to the event of exactly 1 tail. So you could also think of it like that. And then you know that the size of B is equal to, well, 3 by the same idea. You can look at rows 2, 3, and 5. So this implies the probability of B equals 3/8 again. C. Let C be the event. What is the last thing we want to look for? You get at most 2 heads. So that means basically you get at most 2. Remember that means less than or equal to. So that means you get 0 heads or 1 heads or 2 heads, and no more. Notice that this is the complement of 3 heads. Okay, so it would be nice to just find, well, probability of C complement would be 1 out of 8 because there's only one way to get 3 heads. This is row 1. And so that probably is 1 minus the probability of the complement of C, which is 1 minus 1/8, which is 7/8. So that's that one. So I can set up the table once, and I can answer all the questions from that one table. I just count which rows have what I want, right? So that's one method. And it's nice, especially if you don't have a lot of options. Like if we were doing a situation where there were like 50 options, 60 options, I wouldn't recommend drawing a table. I would also not recommend drawing a tree diagram. But with 8, it's not that bad. I feel like once you start getting beyond like 16 rows, then it starts to become ridiculous. I'd probably go up to 16, but I probably wouldn't go any further than that. Unless I'm really desperate and I really can't think of anything else, then don't waste your time trying to come up with something easier. Just do what you can do. So that's a table. Method 2. You can do a tree diagram. We also spoke about this. So this is, say, toss 1, toss 2, toss 3. Okay, so for toss 1 can go 2 ways. Heads or tails. In the first situation, it can go 2 ways, heads or tails. In the second situation, it can then also go 2 ways, heads or tails. And finally, it can go heads or tails. So now you have 8 total options. Which you can figure that out just by drawing the tree diagram. You didn't even have to think about the multiplication rule, even though it still applies. There are 8 edges at the end. So now I know I have 8 total options. And for each one, so for A, probability of exactly 1 head. can have and B probability of, I believe, exactly 2 heads. I'm just setting these guys up here. And C C was the probability of at most 2 heads. Okay. So when we get to, so you have that tree diagram, and you can just draw one tree diagram. I'm just doing this for some sort of clarity because I want to draw the arms, because I can't really describe this as first row, second row, third row. So I want to redraw the arms. So one way to get exactly one head is you can either get the head on the first toss, second toss, or third toss. Is pretty much the idea. So exactly one head, well, I can get a head first, but then because I already got that one, I need to make sure I select 2 tails after. So that's one arm. Or I could not get the heads first, get it second, but then I have to choose a tail after because I already got that one H. Then I could avoid the heads on the first 2 tosses, but then make sure I get it on the last one. So here, you know, 3 arms have what we want. So this means probability of exactly 1 equals 3 out of 8. Get the same answer. The idea behind, so that's what would that? The idea behind B would be pretty much the same. We need exactly 2. So I could also think of this as only one tail. So I can make sure I get a tail and then make sure I pick 2 heads. I can pick a head, then a tail, then a head. That's exactly one tail. And then what I can do is I can make sure I pick 2 heads and then a tail finally. And again, 3 arms have what we want. But you can count these all on the same diagram. But yeah, this means probability of exactly 2 is also 3 out of 8. Similarly, less than or equal to 2. So we want 1, we want 0, 1, or 2, right? So here I have 0. Here I have 2. Here I have 2. Here I have 2. Here I have 1. You'll notice, oh, here I have 1 also. And here I have 1 also. 7 arms chosen. Notice that only H, H, H left out. You could also just realize that. So then the probability of at most 2 is going to be 7 out of 8. Right? So I'll mention here, you only need to draw this once. I'll repeat the diagram for clarity. So another way to get to all the correct answers, 3 out of 8, 3 out of 8, and 7 out of 8 via a tree diagram. So those are the main general methods, I would say. For the other methods, you could so now for the less general methods, so method 3, tons of ways you can do this. You can do this by the slots method. So you just have, for A, you imagine that there are 3 slots, toss 1, toss 2, toss 3, right? And so now you want the, so you know you have 2 choices here, 2 choices here, 2 choices here. This means we have 2 to the 3 equals 8 total choices. Multiplication rule. And by the way, if one of these methods get you more excited than the other one, then that's your method, right? You're like, yo, that's how I was thinking about it, right? It's like you're at a club and the DJ is playing a bunch of songs and yo, that's my song, yo. That's how you should feel about this. It should be that exciting. So if you're like a tree diagram guy, you should be, yo, yeah, tree diagram. Yeah, okay, right? You really want to kind of, you do want to think about things correctly, but at the same time, you don't want to fight your brain too much. If your brain likes the tree diagrams, you should probably just go with tree diagrams. If your brain likes setting up tables, you should go with the tables. Brain likes setting up the slots, you should go with those. So we have that. And now basically you say to yourself, well, how many ways can I get one head? So now let A equals event, we get 1H. Now we want to know how many ways that can happen. Then the size of A, you should realize that it's 3 choose 1. Why is it 3 choose 1? This is the number of ways to choose one spot out of 3 spots in no particular order. Right? I don't care when the one head happens, if it happens on the first toss or the second toss or the third toss, right? I just want one to happen. So I know I want to choose one spot out of 3 spots for the head to appear. And so that's a combination by definition. Like I don't particularly care whether it happens first, second, or third. Order doesn't matter to me. 3 choose 1 is 3. And yeah, so probability of A 3/8. If you move on to B, so you have 1 slot, 2 slot, 3 slot, toss 1, toss 2, toss 3. And this one says, create some more space here. Yeah, we're showing a lot of methods on the first one, which I feel like this was the example that we showed a lot of stuff on last time as well. It's a nice example to illustrate a lot of techniques. So now I want B equals the event exactly 2 heads. And again, by multiplication rule, 2 choices, 2 choices, 2 choices. So 2 cubed equals 8 total choices. Probably wouldn't have to redo that, but just because. So here again, I would just say, all right, I have 3 positions. I want to choose 2 of them to put the heads in. We know that that is 3 times 2 over 2 times 1. So that's 3 ways to choose 2 positions for the H. So then, yeah, the probability of B is the, it's the size of B over the size of S. I haven't been writing that, but it's not important. 3/8 again. You move on to C. We want the probability of at most 2 heads. And I would say let me just write, because I'm going to rewrite this. Let C be the event at most. At most 2 heads. So this is a bunch of stuff to count. So this part means 0H or 1H or 2 H's, right? This seems like a lot. Right, like you'd have to count 3 different situations for this one problem. It's kind of overkill. So that's when you kind of think about complements. And so now you start to think about C complement. Note, C complement means you don't have 0 or 1 or 2 heads. What is the only other option? 3 heads. There's no other option. So now this means that the size of C complement is going to be 3 spots. I want to choose all 3. That's going to be 1. And so the probability of C is 1 minus the probability of C complement, which is that 1 right here. Seven over 8. Right? So notice this one, it is shorter to write, but I want you to appreciate that I kind of have to figure out each problem anew. Like I have to figure out, okay, I want to choose 1 spot here, so I'm going to use this combination, and then you have to think about this. Well, I'd have to choose 2 spots here. We want to figure out how we can do that. I can use the combination again. Here, you're like, okay, I want to pick like 0, 1, or 2 spots, but it's easier to pick 3, and then you could. Right, so we're using the same idea, but then you have to decide how many choices you want to make. It's kind of from scratch, as opposed to here where you just draw 1 table And you can literally just count rows for every problem. Method 4, I would say it's similar to method 3, but write things out more explicitly in terms of tuples. So again, like I'm always going to consider the first position, the second position, and the third position. Going to count the total number of tuples. Then I'm going to count the number of ways I can be in each tuple. But you pretty much kind of imagine the slot idea, but you just kind of write it out as everything being in tuples, where you kind of start by setting things out like this, and then you just basically describe how you're counting things. I don't think there's a point in doing that. I feel like anyone who would think in that way would do it the slots way. Whew. That took forever. Let's go. Problem 4. You toss 2 fair 6-sided dice. Find the probability that you roll a sum of 7, or find the probability that you roll an even sum. You can do this a bunch of ways. So method 1, I would say this is the more general one. I would use the table. And I gave you a specific kind of table for something like this. So this is when we kind of had this idea going, where you had die 1 options and die 2 options. So die 1 can be 1, 2, 3, 4, 5, or 6. Die 2 can be 1, 2, 3, 4, 5, or 6. And yeah, so we have and I can just decide, okay, so this table, I'm going to be looking at sums. So I'm just going to add up the rows and the column. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6, 6 plus 1 is 7. Right, and I keep going like this. So that would be 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Again, you only need to draw this once. But that's all possibilities. Notice that there are 36 total possibilities. Which you could figure out by multiplication rule. Right, because you have for die 1 and die 2, you would have 6 choices and 6 choices, which leads to 6 times 6 equals 36 total choices. So you'll know you can do that anyway. One thing I would say, be careful, don't mix up the labels in the columns and rows with the actual numbers that you want to count. So once you actually do that, everything else is actually going to be pretty easy. So I'm going to copy this just for clarity, but like I said, you wouldn't have to do this all the time. So A, we want the probability that the sum is 7. Okay. So now you want the probability that the sum is 7. You just count off all the 7s. That's basically what it comes down to. 1, 2, 3, 4, 5, 6. There's 6 7s. So this means the probability sum is 7 is 6 out of 36. B. Find the probability you roll an even sum. So probability of even sum. So now you just count off all the even numbers. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. C says, if you had to, what would you bet the sum on a single toss of 2 dice? If I had to guess, what outcome occurred? The answer is we'd guess 7. Anyone know a game where you roll 2 dice and it's a good thing to get a 7? It's called a game of craps, right? You roll 2 dice to get a 7 or 11, you're lucky. Right, which is not as great as you would think. So you'll be like, well, the biggest chance of getting a 7, the biggest chance of getting the number with the largest chance is a 7. But out of the total possibilities, it's not that much by comparative. So let P of I equals probability of getting some I. So notice here, the possibilities are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are all the possible sums that we can get if you look in the table. And I'm really just writing this all out, but you can kind of see there's only one way to get a 2. There's also only one way to get a 12. Either you get 2 1s or 2 6s. If you look at the 3s, there are 2 ways to get 3s. There are also 2 ways to get an 11. If you look at the 4s, there are 3 ways to get a 4s. There are also 3 ways to get 10. Look at the 5s, there are 4 ways to get a 5. There are also 4 ways to get a 9. Notice that they're counting up from either side. Similarly, there are going to be 5 ways to get this and 5 ways to get that. Then you get to 7, which is right in the middle. There are 6 ways to get that. That's the most likely outcome. Right? That's the number that has the biggest chances of occurring. So, I mean, in general, it wouldn't be a good bet because there's only a 1/6 chance that you'd be right if you actually guessed 7. But gun to your head, you had to pick one. 7 would be the one you would pick. Probably a histogram. Hopefully you remember what a histogram is. This is just going to be a diagram where you can kind of see where the probability is being concentrated. So you can talk about probability. Histogram for the sum of 2 dice. Where you pretty much plot the thing that we just saw. So on the vertical, you would put the probability. And on the horizontal, you would put the sum. So the possible sums are 1. I'm gonna need that's not 1. I need a lot of space. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we can go from 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, or 6 out of 36. What you'll notice here is that the 2, you can get it to 1 out of 36 as well as a 12. 3, you can go 2 out of 36 as well as the 11. 4, you can get 3 out of 36 as well as the 10. 5, you can get 4 out of 36 as well as the 9. 6, you can get 5 out of 36 as well as the 8. And then the 7 is the longest one. So you can see that the 7 is where most of the probability is concentrated. That's called a probability histogram. Good histograms always have titles. This is the title of the histogram. Yeah, that's. I hope I'm actually making this shorter as opposed to longer. So of course, we're not going to do these. I'm going to leave them for you guys to try again based on the lessons that were learned here. That took forever, but that's because I'm like doing 4 methods for like problem 1. And I lost the other problem. There was a problem 8 somewhere. Oh, is that it? Yes. These. Any guess as to the third one, the 5th one, problem 5, before we go? You have 4 playing cards, 2 are red, 2 are black. Find the probability that if you shuffle them and draw 2 at random, you get the same color. Right, meaning you get like either the 2 black or the 2 red. Oh, think about it. This one is going to be very interesting because it's going to allow me to segue into a new topic, which is what I wanted to do at the end of today's class. But hey, we'll do those tomorrow, and then we'll talk about the new topic. I probably won't do as many methods for each of these, so we'll get these done out of the way tomorrow. I'll probably do a couple methods for problem 5, but we're going to work slowly through problem 6 using enumeration because I kind of want to tease out a formula for you guys that we're going to be using in the future. And then I'll give you a little bit of theory to wrap up the end of tomorrow's class. So yeah, for now, we'll stop there. So here's how we're applying our knowledge of probability to solving problems. Hopefully that's clear and you're kind of catching on. But now I got to go torture the other class. So I will see you guys in the next one. Ciao.